So following the last set of lecture segments, which were about two-level systems and how we can think about how they might evolve as a two-level system might evolve as a function of time, we get a really good question from one of the students in the class who basically asks, what are real two-level systems? Are there any? And the student mentioned something about, I think, probably NMR, spin, how you can have a spin 1/2 system in a magnetic field. And what I want to make sure that I promised the student that I would work hard to point out how almost any quantum problem can be thought of as a two-level system, provided your experiment is only sensitive to 2 levels at a time. All right, so maybe there'll be more, but the basic ideas are going to be understandable from a 2-level system. All right, now there's a few examples. First of all, in almost any realistic environment that you have, any realistic chemical scenario, it's very unlikely that they will have a true 2-level system. Now, NMR is about as close as it gets. The spin of an electron, a spin of a nucleus that's unpaired, like that has an integer spin. So like a half-integer spin, like a carbon-13 or a proton or N15 or fluorine-19 or a bunch of nuclei that have an unpaired nuclear spin, and then they have a spin moment, and they can interact with a field when you put them in a magnetic field and split the levels. There's more complicated spin states than just spin 1/2. Different electronic states might have spin, like a triplet state, for example. You can make a radical, which has an unpaired electron spin, and then you can address that electron spin by putting it into a magnetic field and splitting the levels of the electron spin. Right, so that would be EPR, electron paramagnetic resonance. And then you can combine the two. You can combine NMR and EPR into some of the most powerful techniques people have right now for those kinds of magnetic resonance type experiments. But once you have one spin and maybe there's another spin around, then they can start to couple, and all of a sudden you don't really have a 2-level system anymore anyway. So first of all, a 2-level system is completely, a theoretical construct, except for a couple, few examples where maybe it's as close as you can get. If you have a single proton in the middle of nowhere, but happens to have a magnetic field, then in fact you will have a spin 1/2 particle with only a up and down and 2 levels. But even the proton on a carbon can have an interaction with the carbon, and that interaction with the carbon might shift the frequency or split it too. Right? So anytime you have one quantum system that can interact with another one, you can think of them as basically a 2-level system with coupling. What I'm going to do now is I'm going to show you a whole bunch of examples, some of which will be familiar and some of which might not be familiar, but nevertheless you will hopefully see how useful they are, where we can adapt a chemical problem to a 2-level system picture. Okay, so the way we can start this out, first of all, I want to say that there is no such thing really as a 2-level system, and there's a few that you can approximate really well. But if we're talking about molecular spectroscopy, vibrations, electronic transitions, electronic states, of course there's no such thing. You add spin, you have a chance. And if you don't do anything that's relevant, that addresses spin, then this is really not an issue, right? So if you never see the effect of the spin, then of course NMR is not going to, the issues that we brought up for NMR are not going to be relevant here. All right, and we have a lot of quantum systems we can solve exactly like harmonic oscillator and particle in the box, which have an infinite number of levels. So it would seem weird to take something where I can have an infinite number of levels and only want to treat 2 of them. And what you'll see is that a lot of times the reason we do this is because we can't really see all those infinite levels. In a harmonic oscillator, we already showed in the problem set that the selection rule is that you have a plus or minus 1 change, right? The quantum number changes by plus or minus 1. Now, even if it's anharmonic and that's relaxed a little bit, it's still dominated by the 0 to 1 transition, or if it was for some reason in an excited state, the 1 to 0 transition, something that you can see in Raman spectroscopy, for example. But most of the time, it's just 2 levels that we're thinking about. All right, so now in atomic transitions, selection rules are a little bit different. In molecular states, they're also different. But you don't usually say, oh, I'm going to go from my ground state to 5,000 electronic excited states, right? You could do that. I don't know what utility that would have. You wouldn't be able to interpret it. So what we typically do is we say, okay, I have a ground state, I have an excited state. There might be vibrations, for example, superposed on the electronic state, as we will definitely discuss a lot. But in general, you are going to be thinking about manifolds, probably 2 at a time. Right? That's very normal. So it's not unreasonable to start with a 2-level system because it's the simplest thing that has 2 levels, where you could see a spectroscopic transition. But what I want to do now is I want to make sure that people see that this 2-level system business can actually be very useful, and useful in a practical sense, not just in a theoretical way. All right, so what I'm going to do is we're going to consider back to a pure 2-level system so you can see what happens when you only have 2-level systems. And then I'm going to show you examples where we recover 2-level systems where we didn't expect to see them probably. Okay, so let's do this. Now, to make this interesting, a single 2-level system coupled to a field of what we've already done is done and dusted. There's nothing else we can do about that. So the thing to make interesting is to think of this like a little piece of Lego. So instead of having just a single 2-level system, I'm going to have 2. All right, now this is where things start to get a little bit more interesting. For my notation, I'm just going to call this 2-level system A and B. Okay, and I'm going to presume that I've solved the eigenvalue problem for the individual 2-level systems, number 1. Number 2, I'm going to assume they're the same. We can change it later, but let's assume that they're the same. It makes some of the formulas a little bit easier. It doesn't make them that much easier. It makes them a little bit easier. Well, we need to list the states. We need to call them something. We need to have a Hamiltonian. So the Hamiltonian is, as you can guess, going to be very simple to start. It's going to be the HA Hamiltonian plus the HB Hamiltonian, right? Just the sum of the 2. And then that's it. We're going to add a coupling, but not yet. All right, so then when we have this, we write down what the solution is of this eigenvalue problem for one of the Hamiltonians, as we'll call it A. So the way I will notate this, I will simply call it, what did I do here? I'll just call it A, yeah? HA. And then you'll have the energy of A. Yeah, that's fine. Actually, no, let me change it. I'm going to change my notation on the fly. This is always risky, but I will do it. All right. So what I'm going to do, I realize that it gets a little bit ambiguous, even though in my head it makes a lot of sense. But what I'm going to do is I'm going to call this A sub n. And then it's going to have energy of the A type, level n, A sub n, right? We need to be able to keep track of the A's and B's. That's why I want to do that. All right, well, then the B one is the same. Now, of course, this is a lot of notation for the fact that I'm only going to have 2 states. But you'll see, I want you to be very clear on what the origin of my notation is. All right, and this is the B type system, Bn. Okay, so this is the important thing, that Hamiltonian H only knows about the A. HA only knows about the A vector. The HB only knows about the B vector. So what we would say is these are 2 different Hilbert spaces. There's 2 different linear spaces. One of them is the Hilbert space that corresponds to Hamiltonian A, and the other one is the Hilbert space that corresponds to Hamiltonian B. Now there's only 2 eigenvectors, or 2 vectors in each of these spaces. So that's why we like this, because you can write everything out. But we start out with that. Now, what we want to do is we want to figure out what are all the possible states of the system that we can have, and how do we make a vector space from these individual vectors that spans that whole set of states. All right, so it's intuitive, and then I'm going to do the math, and hopefully the connection between the intuitive and the math. So one is that you have both of them in the ground state. Right, that's one state of this situation. One is that you have A in the ground state and B in the excited state. Another is where you have B in the ground state, A in the excited state, and then the last one, the only other one, is when they're both excited. Okay, so we can write that down as A0, all right, and as one part, times B0. All right, now you might wonder, why did I write times here? What does it mean to multiply 2 vectors? That seems like a very strange thing to do. Okay, so what it is it's not a true multiplication. Like, I'm not going to get 5 times 2 equals 10 here. What it means is I take the part of vector A, or the Hilbert space of Hamiltonian A, HA, and I combine it with the Hilbert space for B. So we call this, the mathematicians call this a tensor product space. Now, what's an analogy that you might have already seen? So hopefully, I don't think I did it, but you might have seen other multidimensional problems. The most common one that people have seen is a two-dimensional particle in a box, right? Or a 2D harmonic oscillator. That's the other really common one. But believe it or not, you've seen other multidimensional problems. You probably saw the hydrogen atom, which is absolutely multidimensional. The potential is spherically symmetric. And what you found out is every time you had a problem in multi-dimensions where the Hamiltonian could be broken down into a sum of only one or the other, each of the dimensions, with nothing connecting the two, then the eigenfunctions were the product of those two, right? So for example, in a particle in a box, when you have a two-dimensional region in x and y, you write down the Hamiltonian. Well, what is there? There's nothing, right? Because V equals 0 here, so all there's left is the kinetic energy operator. So you have P sub x squared over 2m plus Py squared over 2m. That's the entire Hamiltonian. This is a second derivative with respect to x. This is a second derivative with respect to y, so it's totally separate variables. So the full wave function, or the full eigenfunction, will be dependent on two different quantum numbers, the one on n and x and y. It'll be dependent on the two variables, and it's simply the product. So maybe I'll make a capital for the multi-dimensional one. This is nx on x, and this is ny times y. Same thing for a harmonic oscillator. If your harmonic oscillator is just x squared plus y squared, with the appropriate scalings for the mass and the frequencies. All right, and so this is what you do. Now you saw this also in the hydrogen atom. You have a radial part and a angular part. Similar reason, because there's no coupling between the radial part and the angular part for a spherically symmetric Hamiltonian potential. So anytime you have this situation like this, where you have a single Hamiltonian along one dimension of whatever that dimension is, and another one along another dimension, then the eigenfunctions or the eigenvectors will simply be the products in functions like this, or the tensor product if they're just in the Hilbert space vectors. All right, so this is ground state, ground state. This is ground state, excited state. This is excited state, ground state, and this is both excited. Now, this is very heavy nomenclature when we just only know that each of them has two states. So what you often will do in this situation, I could list these 1, 2, 3, 4. That would be fine. I could do all my calculations just having 4 vectors and just naming them 1, 2, 3, 4, or star, triangle, square, rectangle, whatever you want to do. What people often like to do to maintain the memory of where these sort of labels are coming from is to simply write, for example, that for the ground state, 0, 1 for the second, 1, 0, 1, 1. Now, in this situation, that's all you have, right? 4 total states, 4 total eigenvectors. Now, of course, these are the eigenvectors of this Hamiltonian, but they're not going to be the eigenvectors when we add a coupling term. They're going to get mixed, just like they did with a two-level system and a coupling. What else should we keep track of? So just realize that the order of these matters. So the 0 means it's the A system quantum number, and the second number, the second entry here, is the B one, right? So as long as we remember that, we're not going to have any problems at all. Now, what about the energies? Well, we know the Hamiltonian is the sum of these two. So H operating on one of these states, which I'm just going to call AB now, knowing that A is either going to be 0 or 1, whatever A happens to be. B is only going to be 0 or 1, whatever it happens to be. So that's going to be, I'll write it out really slowly, but later I'm going to go a little faster, right? AB. So we distribute this, and we have HA operating on AB plus HB operating on AB. Now, the operator HA only lives in the Hilbert space, okay, probably a little too sloppily called HA. And HB lives in the Hilbert space for HB. All right, so that way to think about that diagrammatically is that this HA talks to and knows about this entry of the vector, whereas the HB knows about this entry of the vector. Think of it like the partial derivative over here, right? Partial derivative with respect to y does not care what the x part of your function is. It's just going to scoot right through it and do the derivative to the y part, right? And vice versa for the x. So that's a nice concrete way of seeing it. Here is the sort of operational way. Okay, well, we know what to do when HA operates on A because we just worked that out over here. So this is going to be the energy of whatever state A happens to be for the A thing, right? Back gives us back AB, AB again. And then the same thing for the B. So we're going to have whatever number A is, or whatever number B is. So at this point, we could have had the two states have slightly different energies, completely different energies. We'll make it simpler and have them be the same. All right, well, what does that do? This factors out, of course. So we have EA for the A case, EB for the B case times AB, which proves that AB is a solution to this eigenvalue problem. All right, and it has eigenvalue given by the sum of these two. All right, so if we write down an energy level scheme, which we can do exhaustively for this, we can see what our energies look like. Now, let's make the simplifying assumption that, so we're going to say epsilon 0 A is equal to epsilon 0 B, and or whatever E, I guess I'm calling it, E1 A is equal to E1 B. All that means is that we have two identical two-level systems, a very common way to start out. We'll see how you can add in differences in energies. That's going to turn out to be very important, especially for understanding spectroscopy, both, and you wouldn't believe this, vibrational spectroscopy and spectroscopy of really complicated things like photosynthetic reaction complex or photosynthetic antennas, reaction centers, and you name it. All right, that the same conceptual framework applies to both. I cannot emphasize that enough. All right, so let's see here what we want to do then. All right, so we're going to just write these down. All right, so the lowest possible energy is going to be when both are in the ground state. So that's the 0, 0 state. So that would correspond to E0 plus E0. We could set that to be 0 to make it even simpler for us, but we'll just leave it there right now. Then what happens is these two are the same, right? So I take a step up this ladder or a step up that ladder, that's the same energy. So I'll have two degenerate states, right, that correspond to one excitation plus one ground state. There's two of those states. All right, and then the next one up is going to be when I have two excitations. Epsilon 1 or E1 plus E1. And that's it. There's only four states. So what you notice here is there's two states in the middle that have the same energy. Okay? And what we're going to find out is if we add a coupling of a particular type that is the most useful kind in this model, it'll look, the resulting math after we do more than one board extra will be equivalent, identically to if we just started out with these two levels here that were degenerate and added a coupling between them and that will split them apart. Right? So we're going to get, after this, two levels here and here whose energies will be different, provided that we use the type of coupling that I'm going to show you. That is the common kind that people use. Right? This is not a mathematics course on every single conceivable thing that you could do. This is a science course on what people actually really do in real life. Okay, and as you can guess, the amount of coupling is going to determine the splitting here. And then what's powerful about this is even two-level systems have polynomial scaling, like bad scaling, maybe not polynomial. I'm going to have 2 to the n. So if I have n two-level systems, right? So I have 1, 2, 3, up to n. The total number of states in my basis will be 2 to the nth power. Right? And that means my Hamiltonian matrix, evaluated exhaustively with all of these, right, will be 2 to the n times 2 to the n. So that the matrix itself will be 2 to the 2n power. So if n is like 2 or 3 or 4, that's no big deal. But if n is 1,000, you have a problem, right? 2 to the 1,000 is a reasonable, 2 to the 2,000 is a reasonably large size matrix. All right, so although these do scale amazingly well, and you'll see we'll be able to come up with really cool two-dimensional sort of what are called exciton models of two-dimensional delocalized states, and adding in disorder. We can look at the eigenstates in the spectrum, and then we can relate that to real-life complexes such as PS1, the photosystem 1 complex. That's an important light-absorbing antenna in photosynthetic organisms. You might think, how can you go from this to photosynthesis? Stay with me, you'll see. All right, so what we're going to do now, we started out the basics. We have the non-coupled situation. We have our little energy level scheme. We have our looking ahead. Let's add coupling. All right, so now we're going to add the coupling. And right now, the coupling is purely now it's like a kind of mathematical concept. I'm going to talk about how you would have chemical intuition about what coupling comes from in real life as we get through the next section. All right, so how do we do the coupling? So the way we do the coupling in this particular model is one where we only allow there to be one total excitation. All right, and so this is a specific kind of coupling. The jargon of it is not that important. Depends a little bit on the sort of strength of it, but basically it's a model that we can do where we say that we're going to have the possibility to connect a state, and by now a state requires us to specify the state of like the quantum number of each of the two, right? So I'm going to imagine a scenario like this, all right, where the A state is in the ground state, but the B state is in the excited state. Our coupling is going to allow this situation to exchange or be connected to this situation, where A is in the excited state and B is in the ground state. All right. Now you might say, oh, but there could be other things. Fine. That would be a different model that people don't use as much. All right, so we're going to do this model, which is a sort of single excitation model. All right, which is to say I have one excitation of B and I'm connecting that to one excitation of A. Now the question is, how do we make this in the Hamiltonian? How do we turn a term like this on? Now, let's look at what this state is over here. This is the state 0, 1, right? And by state, I mean this corresponds to this eigenvector of the original Hamiltonian without coupling. This corresponds to the situation 1, 0. Okay? So just like when we had the two-level system with the coupling between those two levels, and we looked at something like VEG, EG, plus the complex conjugate, we're going to do the same thing, except now instead of E and G, I have this state and that state. Remember how I said I could label these 1, 2, 3, 4? Okay, so this would correspond to the coupling between state 2 and state 3. Okay, just we write state 2 this way, we write state 3 that way. But it would look exactly like this. Okay, so that means we have a term, a magnitude, an amount, and then we have the algebra part. Right? So here's how we're going to write this. So V will equal 0, 1, and I'm just going to call it, so I'll call this VAB like the operator, and this is going to be some number, right, which could be complex if we want it to. So on the left, it's going to be 0, 0, 0, 1. On the right, it's going to be 1, 0. Plus the complex conjugate. Right? And so hopefully you see the connection between the original coupling that we had, okay, with the complex conjugate. And that's it. This is all you need. This is how you make coupling between two states. And the way to think about why you would have this coupling, one way to think about it, is if I imagine I have a spin for something, like a spin over here, and a magnetic field that comes from the magnet. This is saying that the spin transition between up and down for this spin will depend on whether the spin next to it is up or down. All right? And that is all you need. We will also see examples with vibrations. If I have a coupled vibration, for example, in carbon dioxide, There's no reason that you can't think of carbon dioxide, the carbonyl vibrations in the line of the molecule, as one CO oscillator over here and another CO oscillator over here. That's fine. And then what you can do is you can say, all right, I'm going to think of one harmonic oscillator here, one harmonic oscillator over here, but this is chemistry, right? If I start to pull on this side of the molecule, this side's going to know because of the molecular orbitals, that span the whole molecule. So if I start pulling on this oxygen, maybe I imagine I just extend it to a certain distance here. Now if I start to pull on this one, I'm going to find that the energy change with pulling is going to be different, whether this carbonyl is here or here. Right? That's what we call vibrational coupling or anharmonic coupling. The frequency of this side depends on the displacement of that side. And with that, you can make a model that lets you understand the symmetric and antisymmetric stretches of carbon dioxide and higher excited states that you don't get from just a harmonic frequency analysis. Okay, so let's see what we can do to make some progress about that. All right, so the first thing that we're going to do is we're going to write down the matrix elements. So we need to write down the matrix elements of this thing. Now, I'm going to write down the exhaustive Hamiltonian because we only have 4 basis states. So we know it's a 4x4 Hamiltonian, okay? We know the diagonal elements of the matrix because the diagonal elements of the matrix are going to come from the individual Hamiltonians. But let's just do it slowly so that everybody's on the same page. All right, so I can fit the diagonal elements right here. How do we do this? We're going to write, for example, NM, because there's 2 labels, so we have to write them both. HA plus HB, so I'll do that part first. And I'll do N primed, M primed. As I said, it's a lot of jewelry for the fact that we can only have zeros and ones in here. Okay, but I want you to see it because when we do it for the case of vibrations, there's going to be, still, and then it'll be an infinite ladder of harmonic vibrations, harmonic states. All right, and so what is HA, right? HA only knows about the A part of the system, right? And HB only knows about the B part of the system. And so then what that means is you'll have the N and N primed will have to be the same because it's diagonal for that one. And then the M and M prime will also be the same because there's no operator for them. It's just a constant, right? So then we're going to end up with delta N, N primed, delta M, M primed, and then whatever the energy of N state is. Right? Plus, same thing for the B. The B doesn't know about the N primed. Remember, it's like the partial derivative with respect to whatever the M coordinate is. So it passes right through the N and just talks to this. So that's going to give us an epsilon M primed. Over on this side, when this comes through Tetris style, we're going to get M primed, so that delta's that. And so we end up with delta M, M primed. The N's don't do anything, so they're just deltas, M primed, and then epsilon M. What are these? Well, these are the diagonal elements. When N is equal to N primed, and when M is equal to M primed. Okay, so that would mean, for example, what would be a diagonal element in this case? It would be something like 0, 1, H, 0, 1. Right? So these two are the same, and these two are the same. All right, so now we know that. And then we have the off-diagonal elements here, right? The one on the right will only be non-zero. I'll use a different color. This will only be non-zero when we have 0, 1 over here. And on the other side, 1, 0. And this will only be non-zero. The first term will only be non-zero if we have 1, 0 over here and 0, 1 over here. Right? So this corresponds to the element 1, 0, 0, 1, and this corresponds to the element 0, 1, 1, 0. So when we write the whole Hamiltonian, it's actually surprisingly simple. When you do these kinds of things, here's a trick. Write the basis vector labels around the edges, sort of like Battleship game. Instead of A in number, you do 0, 0, 0, 1, 1, 0, 1, 1. Same thing over here. 0, 0, 0, 1, 1, 0, 1, 1. And then make a little checkerboard. All right, and fill it in. This is going to be the Hamiltonian. We know the V part has no diagonal contribution. So the diagonals are going to be 0, 0. So 0, 0, 0, 0, that's this one. Then the 0, 1, 0, 1 is this one. 1, 0, 1, 0 is this one. And 1, 1, 1, 1. If you get confused about these labels, just call this 1, 2, 3, 4. This is 1, 2, 3, 4. And you'll realize this is the 1, 1, 2, 2, 3, 3, and 4, 4 elements. It's just that we're trying to keep track of the original origin of these different basis vectors. Okay, so the 0, 0 state is going to have the energy of 0, 0 plus 0, 0, or sorry, epsilon 0 plus epsilon 0, so 2 epsilon 0, 2 epsilon 0. The other easy one is over here, right? It's 2 epsilon 1, the excited state, 2 of those. In the middle, we have E0 plus E1. I know I'm saying epsilon and E, whatever. I'm bilingual, I guess. All right, now, what are the other elements that we have? We know that there's going to be a 1, 0, which is here, and a 0, 1, which is here. So that's going to be, I'll put a dot in that element that I know is not 0. All right? Now, we automatically know that we've done all the work, right? Because the rest of it is just the complex conjugate of that, the other side of the matrix, and the others are all zeros, because we didn't find any term that connected the 0, 0 state to the 1, 1 state. Both in the ground state, both excited. That's not in our model. Right? We could add that, but it'd be a different model. So what's the number that goes in here? If we do 0, 1, 1, 0, so 0, 1, 1, 0, that's V. And over here we have V star. All right, and everything else is 0. And that's it. This is literally the most general, except for the fact that the two energies, the two-level systems could have different offsets from each other and different energies. For the case where the two-level systems are exactly the same, this is the most general Hamiltonian for those. All right, and what I want you to notice is something really amazing. Let's look at this chunk in the middle. If you look at this chunk in the middle, what do you see? You see the energies of the two middle states, and you see the coupling between them. That's the two-level system we already did. All right, so what's going to happen, you can work it out when you plug this in and solve the eigenvalues and eigenvectors, that you're going to, in fact, have, I will tell you what the full answer is for those, of course, but what's going to happen is that these two levels are simply going to split apart from each other in exactly the same way that they would split apart if we only had a two-level system with coupling between them. And that is a really powerful thing. Now, I actually don't know who discovered all of this. I do know that some of these models that involve single site excitations are sometimes called Frankel-exciton models. But a lot of these models were rediscovered in different contexts in many different ways. So I don't actually know who thought of this first, but it's extremely valuable. And it's what's amazing about this is if I have more two-level systems, more than just two of them, even though the matrix is going to grow like 2 to the 2n in terms of how many total elements it'll have. So it'll have 2 to the n by 2 to the n elements. The chunk for the first excitation, which is what you almost, a lot of times in spectroscopy, that's all you ever see. First excited state manifold, you could say. That is still going to fit this pattern where there's a little square, or a little chunk of it, yeah, square, that looks like site 1, the two sites, or the two individual energies of their excitations from 0, and the couplings between them. Right? And that's going to be very general. I will show you how this gets you vibrational coupling. And another beautiful model of molecular orbital theory from chemistry called Huckel theory comes directly from this. You can think of all the p orbitals on your conjugated molecule as a set of two-level systems ground state or excited state, occupied p orbital, unoccupied p orbital, and then the coupling that's together by the structure of the molecule. And from this, you can actually get very remarkably close to the molecular orbital theory picture that you would get from doing super fancy DFT with basis sets and everything. I mean, of course, it's not accurate, but the general picture bears out amazingly well. And that's these same models are used to describe when you have multiple chromophores, for example, in a photosynthetic protein, and how they're connected to each other. And it explains how their energy shifts. It can also help you explain why photosynthesis energy transfer is so efficient. And so that's just a few of the many examples that you can do by having what is essentially a coupling between two-level systems. I can map almost any interesting chemical problem onto this problem here.